In this video, I'm going to talk a little bit about ionization. And so most elements that we come across are actually found as part of compounds rather than just as pure elements. The noble gases being an exception because they don't like to bond with other things. So when compounds form, this is when the valence electrons are either transferred or shared between the atoms. So when we have ionization, we have one of the atoms losing an electron and the other one is gaining it. And so almost always it's a metal that's losing the electron and a non-metal that is gaining the electron. And when we have sharing, it's usually between two non-metals. And so we have these two electrons, one from one non-metal, one from the other, coming together to form a bond. And so atoms of the compound gain a stable electron configuration when they do this. This is the reason why they are going to do this, because they are going to become more stable when they do this. So atoms want what's called an octet. So that means they have 8 valence electrons. And so the tendency of atoms to attain 8 valence electrons is called the octet rule. There are exceptions to this rule, so hydrogen, helium, lithium, boron, transition metals. There are actually a lot more of them than that, but for now we'll just think about this in terms of the octet rule, which is that these atoms want to try and have 8 electrons in their outermost shell. And so ions are atoms that have electrical charges, and positively charged ions are called cations, and negatively charged ions are called anions. So you can think of these as the same root words as things like cathode and anode. And they form when an atom gains or loses electrons. Metal atoms, as we saw in the previous video, have low ionization energy, so they are more likely to give up an electron. So for example, sodium, and we saw this with the ionization energy where we see that things in the metals over here on the left are going to have lower ionization energy. It's easier to remove electrons, where the nonmetals over here are going to have higher ionization energy, so it's more difficult to remove electrons from them. So nonmetals have a high electron affinity, and so that means that the nonmetals are going to be much more likely to gain electrons. So again, we see electron affinity, that things over here in the nonmetals, the upper right corner, those are going to gain electrons more easily, where the metals over here in the bottom left are going to be much less likely to gain electrons. And so recall that since each proton has a +1 charge and each electron a -1 charge, if the number of protons is equal to the number of electrons, then the overall atom has a charge of 0. Consider boron, which has 5 protons and 5 electrons. So we have one of our protons and one of our electrons, those will cancel out. We have the second ones, those will cancel out. Third cancel out, fourth cancel out, fifth cancel out. And so when we have all of them canceling out, there is no net charge on our boron. Now, if we instead add another electron, now we have one electron that's not being canceled out. And so that means we have a net -1 charge. Remember, the electrons have a charge of -1, so if we have one more electron, then our atom has a -1 net charge. If there are 2 more electrons than there are protons, then there would be a net charge of -2, and so on. But now, if we instead have one fewer electron, now we see that not all of the positive charges are canceled out. And so we now have a net +1 charge on our atom. And so what we see is that the charge of the ion is just the difference between the number of protons and the number of electrons. Remember, when we have an element, it always has to have the same number of protons, so all we're doing is changing the number of electrons here. And the number of electrons that will change will always be in that outermost shell. So for instance, oxygen, we can gain 2 electrons, and so that becomes a -2 charge. So we have gained this electron and this electron right here, and so now it has a -2 charge. So our electron configuration has a 6 in the 2p orbitals here rather than 4. Whereas if we have something like sodium, now we are going to lose that electron in the outermost shell. And so there is no more electrons in that outermost shell. And so now there is one more proton than there is electrons, so there is a +1 charge. And so now we see that the outer shell, again, we have 2s2 and 2p6. So now there is 8 electrons in that outermost shell, which is the octet rule. These things are always trying to get 8 electrons in the outermost shell. So to think a little more about the octet rule, so this is just that atoms are most stable when they have 8 electrons in their outermost shell, and this is known as the valence shell. and these are known as valence electrons. Atoms will not gain more than 8 electrons in their outermost shell. So this is an important part of the octet rule. Not only that the atoms want to have 8 in their outermost shell, but they will never have more than 8 in their outermost shell. So in reality, most atoms are exceptions to this, but this rule does apply to some very important atoms in organic and biochemistry, such as carbon, nitrogen, and oxygen, so it's often stated as a rule. To get the octet, atoms will either give away, take, or share electrons in their outermost shell in order to achieve the desired 8 electrons in their outermost shell. This is the basis of chemical bonding. And so when an atom achieves an octet in the outermost shell, its electron configuration will actually be the same as the nearest noble gas. So we see this here where these nonmetals that gain electrons try to gain electrons so that it has the same electron configuration as the noble gas to the right, where the metals that lose valence electrons will lose electrons so that they end up with the same electron configuration as the noble gas to the left. So if you go left, then up 1. So if you think about the periodic table as sort of circular, if you can sort of go to the left and then up 1 and then come back on the other side of the periodic table. And so again, what this looks like is if we have something like magnesium, this has 2 valence electrons. It's going to lose those 2 valence electrons and then look like this. So now it has a +2 charge. It has lost the electrons in that outermost shell, and so now it has the same electron configuration as neon, which is the nearest noble gas to the left of it. Whereas if we have something like aluminum, this has 3 valence electrons. It's going to lose those 3. That means it's going to end up with the same electron configuration as neon again. So again, we're going to the left to the nearest noble gas. That's what its electron configuration will look like after it loses its valence electrons. Whereas something like chlorine, which is a nonmetal, it has 7 valence electrons. It's going to gain 1 in order to get its 8. And so now it's going to have the same electron configuration as argon. Where something like sulfur, again, this has 6 valence electrons, so it's going to gain 2 of them to get 8, and so now it has the same electron configuration as argon. So what we see is that we have another regularity in our periodic table where everything in this first column always wants to lose 1 electron to become +1 charged. Everything in the second column wants to lose 2 to become +2 charged. The aluminum at least wants to lose 3 to become +3 charged. The carbon, I always call it kind of a wild card because it can kind of go either way with charge. But then when we get to the nitrogen, now it's a -3 charge. So it's going to gain 3 electrons to become -3 charged. The oxygen column is going to gain 2 electrons to become -2 charged. And the halogens will gain 1 electron to become -1 charged. So this is kind of a good thing to label on your periodic table when you're just learning this, because it tells you what charge these elements will have based on what column they're in on our periodic table. So again, this is just because we're going to gain or lose electrons to try and look like the nearest noble gas. And so what this ends up looking like is with our group 1 elements, like I said, we're going to try and gain a +1 charge. With the group 2, they're going to try and gain a +2 charge. With the group 3, it's going to be a +3 charge. Then we skip over that group 4, which, like I said, I always call kind of the wild card one, to group 5. That's going to gain a -3 charge now. Then group 6 is a -2 charge. Then group 7 is a -1 charge. So these are the charges that these elements will end up with when they become ionized, whether they are losing or gaining electrons. So when atoms gain or lose electrons to form compounds, remember, ions are formed, and that means that we can form what are called ionic compounds, which we'll talk more about in the next few videos. Ionic bonds are then formed, where ionic bonds occur when the valence electrons of atoms of a metal are transferred to the atoms of nonmetals, so that our metal becomes positively charged and our nonmetal becomes negatively charged. They then have an electrostatic attraction to each other, and so they will form what's called an ionic bond. And so that looks kind of like this, where we have the metal losing an electron to the nonmetal, then we have this positively charged ion and this negatively charged ion that will then attract each other because one is positive and one is negative. When atoms share electrons to form compounds, then they form what are called molecular compounds, which we'll talk about in a future video. And these are called covalent bonds. And covalent bonds form when atoms of nonmetals share electrons. So we see now this one has this one unpaired electron, this has this other one unpaired electron. Those will then get shared with each other, so both of them now have their full octet. So we see this nonmetal on the left has 2, 4, 6, 8. This nonmetal on the right has 2, 4, 6, 8. So again, they're always trying to get to that 8 electrons in their outermost shell. That is the octet rule. But anyway, we'll talk more about this ionic bonding in the next few videos. I hope you found this helpful, and I will see you then.